Hello guys, so welcome back to our lab 6, and this is the third experiment of this lab, which is negative half wave rectifier. Okay, so we're gonna implement exactly the positive half wave rectifier, except for that diode here will be flipped. So if we explore, let's go back to the experiment 1. So look at the diode now. So B was toward or connected to the positive terminal of the input, and the N was connected to the terminal of the resistor. Now, in this experiment with the negative half wave rectifier, we just flipped the diode. Okay, so the N now is connected to the positive terminal of the input, and the B is connected to the resistance. So basically, the negative half of the sine wave input will pass, and the positive half will not pass because the diode will be reversed at that time. We will just repeat everything similar to the first experiment, except we'll get flipped result. I mean, we're gonna get negative DC, not positive DC. We're gonna pass a negative half, not the positive half, and everything is like this. So let's run this simulation. Let's measure the input. Of course, the input is still the same; it doesn't change. And then we measure the diode voltage. So in the beginning, we're gonna measure the clipping. So the clipping should be at oh, this is the resistor. Okay, so for the diode, we should cancel B or make it 0 and make this at 2, just like the setting in here, this setting. So look, guys, we know from the lecture that there will be negative clipping at minus zero point 0.7 in the negative half wave rectifier, and here is a negative clipping. So let's measure this. Let's go to min. It's minus 800, around minus 800, which is very close to 0.7. Minus 0.7, of course. The theoretical values that we explored in the lecture. Now let's check the overall signal of the diode. We're gonna make this scale at 100, the voltage per division. And here is exactly what we get in the lecture. Okay, again, since the hip here or the maximum here, the tip is let's go to the maximum here. It's 155.4. It's really very, very, very large or greater than the negative zero point 0.7 clipping. Then this negative zero point 0.7 clipping is not noticeable at all, not observable at all. You cannot observe it. It's really hard. And again, that's why the ideal diode model, really works with such circuits. Okay. Uh, Now let's measure the voltage on the load. Here is the voltage of the load, and as we see, the load only sees the negative half of the sine wave, the input sine wave, and this will result in a negative DC. So let's measure the minimum. Of course, I mean by minimum this point here. Okay. So let's set the trace first to B, then set this to min. It's minus 154. Minus 154 is basically, you know, since there is a clipping at 0.7 for the diode, minus 0.7 for the diode. So the overall max or min here is minus 110 square root of 2 minus 0.7, which is, the diode voltage. This will give us, 154, which is close to what we get here with some very small error. Okay. Now we measure the DC voltage. Here is the DC voltage. It's exactly what we get from the positive half wave rectifier. It was there in the positive half rectifier 49.1. Now it's minus 4, minus 49.1. Okay, and here is the theoretical value. And again, this is VM minus 0.7, but we're gonna put a minus before that. Okay, it's basically the negative DC that we get. So now we measure, we add both together just to verify Kirchhoff, as we usually did. So we're gonna go back here and choose add and apply them together. Then single, and here it is. This is basically the input. If you open the input here, we have the same scales out there, so it should be very similar. Okay, guys. Thank you very much for watching this video. And in the next video, we're gonna, change again the breakdown voltage of the diode. And again, this will affect the DC output here. It will be reduced. Okay, thank you very much. Bye-bye.